Alright, good evening everyone. So it's 8 o'clock. I don't know if this is actually loud enough, but we'll get it loud enough. So welcome to the Great Place and welcome to Science on Tap. My name is Monica and I am a representative of the Women in Science and Engineering at UCSC. And we put on Science on Tap every month in collaboration with the Great Place, where we bring usually a local either academic or scientist or sometimes international speaker to the Great Place for a free talk. So thank you all for coming out tonight. And tonight is my pleasure to introduce Professor Gary Griggs. He's a professor of Earth and Planetary Sciences, distinguished professor, and is also the director of the Institute of Marine Sciences. And I don't know if you grew up in California, but you got your bachelor's in Santa Barbara, and then went on to get his PhD at Oregon State, if I'm correct. So I'm excited for his talk tonight, and hopefully it's a good one. Hopefully it's a good one. He's already given a talk today already, so yeah. All right, so without further ado, let's bring Gary to the stage.
Well, the bar is low now, okay? I did actually speak earlier today at Dominican Oaks. People know Dominican Oaks? They're actually really lovely people over there. Elevate maybe I should be a little closer. Okay, I don't know if you could
lift it up,
control the volume.
walk with it.
I'll just... That's good. Okay? Better. I can hear you now. Actually, the first time I went over the talk, I was asked by the woman, Margie, who handles all the talks, and she had another person from the campus over there, Mary Silver, an oceanographer, and she called. I didn't know Margie, and she said, I had this colleague of yours, and she was wonderful, and they loved her, and I think they'd really like you if you would come to speak. And by the way, I took your oceanography class back in 1971, which dated both of us. So as I went to speak today, they give the talks are right after lunch, and these are generally people older than we are. And I just started, I'd not gotten 3 words out, and the lady in the front row who was sitting with her walker, her head just slumped. So I'm hoping tonight, despite what Monica said, that it's a good talk. So, I think it'll probably get clearer as it gets darker, but we'll do this as it comes. So, I want to bring together 3 topics tonight that are intimately connected: climate change, sea level rise, and the California coast. And the one thing I will tell you, because we're in the middle of a election and conventions and so forth, is climate change is not a question. We don't get to vote on it. It's happening. No matter which party you're in, all carbon dioxide molecules trap heat. They don't have political preferences. That aside. So today, the people of the planet and California are trying to solve 3 problems together. Satisfy a growing appetite for food and water and energy, trying to preserve some sort of a livable natural environment, and also build resilience to natural hazards and extremes. And I really want to talk about the third, but those are all kind of big problems we're facing. I'm going to assume you all have undergraduate degrees in geology, okay? That is a given. So we know the Earth is about 4.5 billion years old, and we think today, about 100 million years after the Earth formed, it was hit by a planetary body, maybe the size of Mars. And this actually came from work of a UC Santa Cruz earth scientist and another group a couple of years ago. And that did a couple of things. As that body hit the Earth, they were both molten. The denser, heavier material sort of added to the core of the Earth. As that planet sort of glanced off, it actually took a lot of the lighter superficial material, so the Earth's crust, the continents don't really completely cover the Earth's surface. But it also knocked the Earth off kilter, off its sort of nice smooth orbit. So what that did was produced the beginnings of climate change. So when that impact occurred, three sort of patterns developed in the Earth's rotation and its orbit around the sun. The first was, in the bottom picture here, the Earth actually has a wobble on its axis. And that wobble has a cycle of about 26,000 years, and then it returns to where it was before. The Earth has a tilt on its axis, which gives us the seasons. But that tilt varies by a couple of degrees. So there are times when it's tilted a little further away from the sun and when it's tilted a little close to the sun. A cycle of about 41,000 years. And in addition, the orbit of the Earth around the sun isn't a circle, but it's an ellipse. So we get further away and closer, and that is a cycle of about 100,000 years. So those three cycles are all working, sometimes together, sometimes in opposition, to make the Earth cooler or warmer. So that's the beginnings of sort of climate change, which affects sea level rise. And this is all totally independent of this gas we're burning tonight, okay? Carbon dioxide. So we now know climate changes have been occurring ever since that impact. We've had climate changes for over 4 billion years on the planet. They've been recorded a number of different ways. Probably the longest records we have are from the deep sea. So as the ocean temperature changes, the life in the sea changes. And we can see that even during El Nino years. We have squid or anchovies or sardines, and we have warm plankton and cold plankton. As those organisms die, their shells accumulate on the seafloor, and we've now gone back into the deep sea. The ocean drilling program's been going for 50 years almost. As those cores have been extracted from the ocean floor, we've been able to determine cool periods and warm periods, going back tens of millions of years. Really good records that have been sorted out over time. Over the last several decades or so, we've been actually coring into Greenland and Antarctica. And the ice is another record of climate change. So not only when snow falls, molecules of air will be stored in the ice, so we can go back and see what the chemistry of the atmosphere was at that time. And there's things like volcanic eruptions that are preserved. So that ice has been accumulating. In the Antarctic, we've now drilled down almost 2 miles. We've gone back 850,000 years of constant record. On a shorter term basis, we actually have bristlecone pines in sort of southeastern California that live 4,000 or 5,000 years, and tree rings are pretty good indicators of climate. It works. And we also have coral that we can detect climate going back several hundreds, maybe 1,000 years in their layers. And we have pollen records. So there's a good record of climate beyond the temperatures we recorded for the last 150 or so years. They go back millions of years. So the last several million years have been characterized by ice ages. The last one ended about, speaking of ice, the last one ended about 18 to 20,000 years ago, and during the peak of the last ice age, we took about 10 million cubic miles of water from the oceans, and we put that on the land as ice caps, ice sheets, and glaciers. So we lowered sea level about 350 to 400 feet. That's where we got all that water. So we know ice covered most of good parts of North America, scoured out the Great Lakes, Cape Cod, Martha's Vineyard is all glacial deposited material. Ice came down over the Pacific Northwest. Seattle was actually under 3,000 feet of ice the last ice age. So for some comparisons here, I just took the Space Needle at 600 feet, and we had ice 5 times that thick, covering Seattle.
Wow.
Alaska, Canada, Siberia, Scotland, Northern Europe, Scandinavia, we're all covered with ice. And so that ice came from seawater, transferred onto the continent. So that raised sea level and lowered it many times. If we look at the history of sea level, and this is just going back, I'm not going to use too many graphics because it's evening, you guys have had a couple of beers, it's stressing your concentration. So if this is 0, 50,000 years ago, 100,000 years ago, 200, 300, this is going back about 375,000 years. And this is where sea level was. So 40 meters below the present, down to 120 meters, 350 to 400 feet below the present. So sea level has risen and fallen as climate has changed. When it's warm, ice sheets and glaciers melt. The water runs into the ocean. Ocean level rises. The other thing that's happening is seawater warms, it expands. So your water heater has a little space on top so you don't blow it up when you heat up the water. And these cycles look somewhat regular. And it turns out this is about a 100,000 year cycle. Those fit with that Earth's orbit around the sun. That 100-year cycle, 100,000 year cycle. Then there's some sort of roughly 40,000 year cycles here, which are the tilt of the Earth on its axis, and the 20,000 year comes in here. But when you put those together, they don't line up perfectly. But these sea level cycles are tied into those climate cycles. This could also be a temperature graph. So 3% of the water in the ocean, roughly 10 million cubic miles, was put into the ocean, taken out of the ocean repeatedly. So roughly 18,000 years ago, sea level was close to 400 feet lower than today. As it warmed, sea level rose back up to where it is today. But what's fascinating is, so by convention, we say where the ocean is today is 0. However, if you would have been here 15,000 years ago, it would have been a whole lot lower. And if you'd have been here 120,000 years ago, it was about 20 feet higher than today. Just gets you thinking about, we're not in a particularly normal time. We're in a very high sea level time, but it's going to get a lot higher. Actually, that was one of the questions I was going to ask you. If all the rest of the ice on Earth melted, would we be underwater here? Good. Not good, but yes. So trying to put that into some perspective, what's driving that today, which is changing beyond all those tens of thousands of year cycle. This is from the longest ice core in Antarctica, which goes back, well, down a little over 2 miles and goes back 850,000 years. Again, in that, those little bits of atmosphere that are trapped in the ice that we can extract when we take those cores, we can actually analyze that trapped atmosphere for carbon dioxide. So carbon dioxide is a little bit of the atmosphere. Most of it's nitrogen, most of the rest is oxygen, which we breathe, but a little bit is carbon dioxide. So this has been the concentration of carbon dioxide, and again, these are roughly 100,000 year cycles. Again, tied into warming, cooling, and that's a feedback loop so that when it gets warmer under these sort of orbital conditions, a couple things start to happen. As the ocean gets warmer, it lets off CO2, so we increase the CO2. Permafrost starts to thaw, and that releases carbon. So there's some things that begin to happen that sort of feed back. The other thing that begins to happen is the ice starts to melt back when it's warmer. The ocean absorbs heat, whereas ice would have reflected it. So once it starts to get a little warm, it starts to get warmer. So what's been happening when we've drilled down in very recent times now, CO2 is increasing. So we're now up to Actually, the most recent measurements from last month were 406 parts per million. So it's now about close to 40% higher than it was ever in the last 850,000 years. So this is not just driven by natural processes. It's way out of line with anything else we've ever had. And there's some numbers here. What if we try to deal with carbon dioxide and burning fossil fuels? We can try to reduce that before it gets a whole lot higher. And if we don't, it could get double or triple. And those bring on other consequences. So this is where we are now based on measurements out in Hawaii. And where's that coming from? Probably things you all know. This is going from 1800 to essentially today. The black line is all the carbon dioxide we're emitting, and the blue is from burning oil, the green is from burning coal, the red is from natural gas, and actually something most people, but you are not definitely most people, don't appreciate is making cement produces huge amounts of carbon dioxide. So the cement industry, which China is greatly expanding, and we have made our own share of cement over the years at Davenport and actually the UC Santa Cruz campus. 1 ton of cement, making it, produces 1 ton of carbon dioxide. So we actually take limestone, which is calcium carbonate, we heat that in kilns, you see those coming onto the campus, and you drive off carbon dioxide and produce calcium oxide, which is lime, which is a building block of cement. So every time we make another ton of cement, we produce another ton of carbon dioxide. So that's of concern, but not quite like coal and gas and oil. So even if we were to completely eliminate all those emissions tomorrow, we're still going to live with the consequences of what's in the atmosphere for probably hundreds of years. It doesn't come out of the atmosphere that quickly. So we're generating probably 90% or so of that from burning fossil fuels and cement. Land use changes, burning of tropical rainforests. I mean, what's happening in Big Sur this week is producing a lot of carbon dioxide. Where is it going? Fortunately, we have a few buffers. A little over half goes into the atmosphere, those measurements that we're getting from the ice cores. Maybe 30% is being taken up by terrestrial vegetation, and about a fourth goes into the oceans. About 1 million tons an hour goes into the ocean. Is that having an effect? It is. It's making the ocean more acidic, and that's a whole nother question and talk we won't get into. But you can't produce that much carbon dioxide without having some effects, and we're doing that and have been doing it on a pretty big scale. A really interesting project that started back in the 50s, the then director of Scripps Institution of Oceanography, Roger Revelle, who was a really well-known scientist, thought back in the 50s that carbon dioxide was increasing and that was going to be affecting climate. So he sent a young guy named Charles Keeling to Hawaii. Said, oh, do I have to go to Hawaii? Okay. And they put up an observatory on the top of Mauna Loa to measure carbon dioxide in the atmosphere. The reason they picked Hawaii is because there's not a lot of industry, there's not a lot of power plants. You could get a good reading. So he started measuring it every day. In fact, what you can see, well, Charles got the National Medal of Honor from the president. He died a couple of years ago, and now his son has taken on the same project. But what you can see is the trend of increasing carbon dioxide. When he started back here, maybe 315 parts per million, but the pre-industrial is, under 300. You can see not only it's going up every year, but the rate is going up also. So we're not only increasing it, but we're increasing it at a faster rate. So even, thank you if you drove your Prius tonight, but we've got some big steps to take to stop that rise. So we're up at something like 406 parts per million. I mean, we can't feel that, we can't breathe it, but we can measure it and we know what it's doing. So I'm going to drop something on you here. Wonderful thing about science is it's true whether or not you believe it. The other is everyone's entitled to their own opinions, but not their own facts. And then I'm going to show something that may offend a few of you, but then we'll go on really quickly. The kid asked his dad, "What's science?" And the dad said, "I don't know, son, we're Republicans." Okay, we'll go on. And I brought it tonight, if you read the Republican platform on climate change, you'll understand why that's important to understand, because basically it's undoing anything that's ever been done. And again, climate change is something you don't have a choice of believing in or not. It's happening, and it's pretty clear. So bringing the sea level up closer to the present, this is going back to the end of the last ice age, and this is sea level. So we can see it rose pretty quickly. In fact, over the period from about roughly 18,000 years ago to 8,000 years ago, it rose pretty quickly as all that ice melted and flowed into the ocean. Sea level rose at a rate of almost 4 feet per 100 years. Today it's rising at about 1 foot per 100 years, so 4 times faster than today. Within that, there were some pulses. And we think today, we're not sure, but this is perhaps when a big ice sheet in Antarctica broke off. And there's a lot of scientists trying to look at these glaciers in Antarctica, trying to figure out what's going to happen next. Is there a tipping point? And there's some evidence that sea level rise is getting warmer, these big ice sheets are starting to float and may break off and so forth. So we think during those periods it may have been rising as fast as 6.5 feet in 100 years, or almost an inch a year. And then something interesting happened about 8,000 years ago. Sea level pretty well leveled off, rising very, very slowly, maybe a millimeter a year. And that corresponds to virtually the entire period of human civilization. Sea level was pretty much zero. Today, it's rising at about 12 inches per century, but all indications are that that rate's going to go up. We don't know how fast, and I'm going to say that I think that curve may be the biggest challenge human civilization has ever had to face. And I want to tell you why I think that's the case. So, again, virtually all of human civilization took place when sea level was constant. So we built harbors and began to build cities and settlements near the ocean for a bunch of reasons. It was often fertile agricultural land like the Nile Delta. There was access to water, ameliorated the climate, and so forth. But that's changed over the past century. And this is a short little video. It's about an hour and a half. No, it's really quick. And this is just depicting what sea level has done in the Central Coast over the last 18,000 years. So it starts way offshore, the Farallones. 18,000 years ago, we could have hiked out there in a very long day, maybe 25, 30 miles. But this is moving forward. In the bottom left, it'll just show you how many thousand years ago it was, and you'll see how that sort of begins to encroach on the present coastline. So we're up to 14, 17,000 years ago.
And then so it's just a combo, and then the tender your salad.
So you can watch it enter the Golden Gate about 8,000 years ago, all the way up the Sacramento River. It's a little slow tonight.
Because it's cold. All the way up to Sacramento.
And then a lot of sediment came down, erosion, gold rush, and so forth. So we see the present situation. But the important point is that 18,000 years ago, this was the shoreline. You can see Santa Cruz down here, and it's migrated in. So the coastline of Santa Cruz was 10 miles offshore 18,000 years ago, and that's the same situation globally. So it's not, this is something new, it's been going on for a long time. Natural environments have adjusted to that, whether it's coral reefs, mangroves, eelgrass, whatever. they have migrated back and forth as sea level has risen and fallen over millions of years. So we worry sometimes about the natural environment. It'll take care of itself. The problems we have is cities don't adjust very well to sea level rise. In fact, they don't adjust at all. So whether it's New York or Singapore or Hong Kong, 8 of the world's 10 largest cities are built on the coast and are quite close to sea level. In fact, many of the rest of the big cities in the top 20 or 25 are coastal cities for the reasons we've talked about. So how do we deal with these? And we learned a little bit from Hurricane Sandy what happens when sea level rises 8 or 10 feet. Well, it comes into the subways and so forth and so on. There's an interesting study I ran across a couple years ago, and this guy, Thomas Shepard, wrote a book in 1912, a little over 100 years ago, and it was called Lost Towns of the Yorkshire Coast of England. And Yorkshire Coast is sort of the east coast, central east coast of England. It's all very soft and weak glacial sediments because this area was partly glaciated. And he discovered 31 towns that had names. They're sort of English names, you know. I don't know. On kinds of weird stuff that have been lost since the time of the Romans. Sea level rise, the coast has migrated about 2 miles in, and all these towns have completely disappeared. So I've been finishing up a book called Coasts in Crisis, and it's trying to deal with not only natural disasters, but also the way humans have affected shorelines. And I decided, instead of just writing only about California, which I tend to do, I would look a little more globally. So my wife and I went to, last fall, we spent September driving around the entire coast of England and Scotland, and then October driving around the whole coast of Spain and Portugal, just to see how they were dealing with the coast and what it looked like. And this was a spot I really had to see. So we got to the Yorkshire coast, and there's all these roads that go out and just stop. And this is one of them. There's a trailer park here, a caravan called Cliff Top Caravan Park. Very much like Deanza Mobile Home Park by the Marine Lab, except this is eroding a lot faster. And we drove out and walked out on the edge, and these are these glacial sediments that are eroding at about 6 feet per year. But interestingly, what they've put there are not only sort of summer caravans, as they call them, or travel trailers, and when going gets stuck, they just move them in. So if you go onto Google Earth, they have, these are all trailers. There are thousands of these, so instead of building homes, they just bring these trailers out there, and they have casinos and swimming pools and grocery stores. It's like cities out there. In fact, they have wheelchair races. We saw people racing in wheelchairs. It was kind of cool. But they're stacked up right along the ocean. Here's another one from Google, and here's one that's the best. But you can see these were the pads where these trailers were. And as the cliff gets close, they just take them and move them inland and buy the next sheep ranch. So in some ways, it's a resilient coast. I'm not advocating this for the coast of California, but it's an interesting way of responding to a rapidly eroding coast. I was inspired by that book to write an article called Lost Neighborhoods of the California Coast, because people think they're not going to move back. We've never done that. In fact, we've been doing it for a long time. This is Pacifica. This is actually a place called Gleason Beach up on the Sonoma coast, where an entire development of homes is falling into the ocean. And we have our own stories in Santa Cruz County, but this is something we're going to probably have to start getting used to. There's some other shorter term things that we can see. We don't have to go back 2,000 years, but places you may well know. Deepak and I did a book a couple of years ago called The Santa Cruz Coast Then and Now, and we found a lot of old photographs and went back to try to find. So these are, find the same spot today. This was Wilder in 1890. Actually, if I show this picture first and ask people where it is, they say natural bridges, because people remember natural bridges. So we're just going to kind of fast forward from 1890 to 2006. And you've probably been out there or walked around the coast. And I don't know what happened to that horse and the buggy, but things are changing, and in some ways they change episodically. We talk often in terms of erosion rates of a foot per year, 6 inches, but we don't lose a foot every year. We lose a big chunk all at once. Place you may know better, natural bridges. 1890 had 3 arches, and by 1972 the outer one had collapsed, and then not too many years ago, the inner one collapsed. So the state parks program doesn't know it, but it's actually now Natural Bridge State Park. There are no bridges left. I don't know if I told you, if I didn't tell you it was Lighthouse Point, it would be hard to tell where this is, but there was a well-developed arch there. In 1885, a few years later, it collapsed. And if you go there today, you find just this little stub, the base of that arch. Everything else is sort of moved back, and they've now put rock in there. But we can see things happening even over our own lifetime. Not long after I came to Santa Cruz, I was up actually surfing at 4 Mile Beach. You may know that, just 4 miles north of town. And I just happened to take a colored slide, and I just was looking at the coast and took this picture. I came back maybe 18 years later, and an arch had opened up at the down coast end of 4 Mile Beach. And then I came back a couple years later, and that arch had already collapsed. So even in 40 or 45 years, we can see change taking place. Now there's just Brussels sprouts out here. There aren't houses, so it's not a big deal unless you're really in love with Brussels sprouts. And then more locally, Capitola, 1972 photo shows, actually there was a duplex here, the Crest Apartments, and you could drive along Grand Avenue in 1972. But by 2010, the house was gone. 6 units of the apartment were taken down after the earthquake, and if you try to go along Grand Avenue today, you end up in the water. In fact, you can't even walk along much of it today. So this is eroding at about a foot per year on average. I have a couple of friends that live out here and want to know what I think about their survival of their house. And I actually have a friend who lives right in here, and I went out there once for a get-together. I didn't know he lived there, and as I looked at his distance from his front doorstep to the cliff, I went, oh my God. His name is Tom. I said, Tom, why didn't you tell me before you bought this house? This is what I do. And he said, Gary, I didn't want to know. He's not worrying about handing it down to his children. He's just going to enjoy it as long as he can. So it's kind of a hard argument to make. If he would have been buying it, I might have said something else. But this is for a number of reasons. There's an undercut at the base of the cliff here. There's a very weak unit in the sandstone. The cliffs are jointed or fractured in a direction that runs here from here directly to New Brighton. So it's almost like playing cards stacked up or dominoes that keep failing. So it's a very difficult area to protect, no matter how much your house is worth. So trying to look a little bit into the future. 2010, then Governor Schwarzenegger got together the governors of Oregon and Washington, a number of state and federal agencies that began to get concerned about sea level rise on the California coast because we have power plants, sewage treatment plants, bridges, airports, harbors, parking lots. Parking lots are easy, bike trails are easy, but those big investments, and we keep building more. They wanted to know what sea level looked like in the future, and they went to the National Academy of Sciences, which is sort of our federal organization for doing objective, unbiased science. They do a lot of different studies over the years. Actually, National Academy was originally created by Abraham Lincoln after the Civil War, during the Civil War, as an independent group to look at major questions. And they usually pick a dozen or so people who spend a year or two looking at existing information, writing up a report that then becomes the basis for future action and policy. So for some reason I was asked to be on that committee. It was an amazing experience with a lot of really smart people. I'll just leave it at that. And so we were asked to come up with global and state numbers for where we thought sea level would be in 2030, in 2050, and 2100. So if we go back in time, this is sort of geological evidence that sea level hasn't changed very much. We see things that live close to sea level that have been there for a long time, oyster reefs, coral reefs, and so forth. Beginning in the late 1800s, we started using tide gauges. So we have, California coast has about 12 of those. Around the world there are dozens, and basically these are water level recorders that were originally put in for ships and showing how much clearance we would have at different tidal stages, when harbors would be safe to enter. But in addition to recording high and low tide, we noticed the water level in them was also changing over time. So tide gauges were used to put this curve together, and the average globally has been about the thickness of a dime per year for the last century. 1.7 millimeters, that's about 8 inches in 100 years. Not anything to worry about unless you live within 8 inches of sea level, but most people don't. The problem with those tide gauges is they're anchored onto land. So we have one at the Golden Gate that's on bedrock. We have them in Santa Barbara and Monterey. Santa Cruz does not have one. Eureka, Santa Monica, San Diego. They're anchored on land. So they're telling us what's happening between the land and the ocean. If the land is rising or the land is sinking, then it's going to give you a relative value. So for example, in Alaska and in much of Scandinavia, they were glaciated during the Ice Age, and that those thousands of feet of ice actually depressed the continent. Sort of like you sit on your mattress, the mattress goes down, you get up, the mattress comes up again, only it happens very, very, very slowly. So the land was depressed. Alaska is still rising. So in Alaska, sea level's rising, but the land is rising faster. So relative land, the sea is actually getting lower every year. So they're not worried about sea level rise in Alaska. In contrast, in New Orleans is sinking. The delta's subsiding from all the weight of sediment. They're pumping out water. Sediments are consolidating. So in New Orleans, here's the global rate, but New Orleans is sinking. So in New Orleans, it's much, much faster. So we knew this was an average, high and low, and it isn't always, all these tide gauges aren't geographically representative. So somebody that I think would be brilliant actually discovered that we could measure sea level rise from satellites. So basically, by putting up a couple of satellites where we know from people who are much smarter than I am exactly where that satellite is, down to millimeters, they actually are using radar and bouncing it off the ocean surface over huge areas to get an average elevation of sea level, and they're able to tell down to a fraction of a millimeter what the level of the ocean is. I find that truly incredible. I mean, I also find cell phones kind of incredible, and texting and all that other stuff is incredible. So the fact that we can also send things to Mars and drive around and take pictures, so it's all part of that whole thing. But what that has showed since 1992 up to the present is that rate is almost double. So this is now taking away all the individual tide gauges and getting an absolute number. So the question is, what happens next? So there's two curved paths here. One is called model and one is called empirical. So this committee was challenged to try to figure out where sea level might be in the future. And there's a number of models out there. Modeling is sort of a big deal today. We model everything: the economy, costs, oil, climate. So there's a lot of different models, a lot of different parameters, but if we add in so much more carbon dioxide, how much warmer it would get, how much more ice will melt, how much warmer the ocean will get. And there's a range of values because, quite frankly, it's not that the models aren't any good or we don't know what we're doing. We don't know how much carbon dioxide is going to go in the atmosphere. Those are social, political questions. They're not scientific questions. Is China going to build more coal-fired power plants? What are we going to use for fuel? The other part of the approach was empirical, where we actually went back in geologic time and said when global temperature was X, sea level was Y. It integrates all those other questions as well. If it gets this much warmer, that's how high it's going to be. So the questions is, as you can see, the further out we go into the future, the more uncertainty. Those are big uncertainties. That's from, in 2100, from say 16 inches to 4.5 feet. And the best way I can the best analogy I can make here is if you were, I'm trying to pick an average age here. Well, let's say you're a young parent probably some young parents. So your kids are 2 years old and you're trying to figure out what's it going to cost for them to go to college 18 years in the future. How much money do you need to save? Well, gosh, tuition's going up really fast. Say today it's $30 or $40 or $50,000 a year. Is it going to be $75,000, $100,000, $1 million? How much do you save? Well, we don't know. So it's not that we're irresponsible, we just don't know. Or you're trying to save for retirement 30 years into the future. How much do you save? Well, what's the price of fuel going to be? What's interest rates on houses? So these are really tough questions, and so we had a big error bar the further out we go. In fact, that's the range, which is huge. So I was trying to come to grips with uncertainty. My favorite climatologist. Now, if I show this to a group of students, they won't know who he is. You will all know who this is. So I think this had to do with weapons of mass destruction, if I'm not mistaken. But there are the known knowns and the known unknowns and the unknown unknowns. And that's a lot to that has to do with climate. We know some things, and then there's some things we don't know yet. So what's driving sea level is basically, we think this committee that ice melt is about 2/3 of it. And again, Antarctica, Greenland, glaciers, a big chunk of sea level. Changes in the density as seawater warms, that's about 1/3 of it. And then there's a bunch of other things here that make it really complicated. Locally, the land can be rising or sinking. We take glaciers off and it rises, and we've got some other things. But these are the two big ones, so it can vary from place to place. So I should have asked you this question, but mountain glaciers, whether it's Patagonia or the Alps or the Andes or the Himalayas, if we melted all of those, sea level would only rise 2 feet. Not bad. We could deal with that in most places. Not the Maldives, a few others. If we melt all of Greenland, which isn't going to happen tomorrow or the next day or the next year or the next year, there's about 22 feet of sea level rise equivalent. How about Antarctica? A lot. Good number. About 200 feet. So that's where most of the ice is, and that's why I asked earlier if we melted it all, would we be underwater here? Yeah, we're probably at, 50 feet or something. So, but again, I'm not trying to frighten you. So we have maybe 225 feet of total sea level rise. Now that has happened in the geologic past. We had a period called hothouse Earth when we think most of the ice on the planet melted. Things are extraordinarily warm from some interesting set of conditions with methane released from the ocean, and things got really warm. Nobody believes that's going to happen in the next century, maybe even not the next 1,000 years, but there's a lot of uncertainty. So we were just trying to give projections. And those numbers are sometimes a little hard to get, but what's 15 inches, what's 24 inches? The question is, how do we turn this off? But I want to look at a national level. So these are tide gauges around the country, and you can see they vary depending on what the land is doing. So we have like Los Angeles, which is actually uplifting a bit. In a century, it's only about 4 inches. Monterey, 7 inches. Louisiana, 4 feet. Washington, D.C., but they're not necessarily concerned about it in Washington. One of the problems on the East Coast is there's a lot of subsidence, so they are actually experiencing now a lot of what is being called tidal flooding. Streets are going underwater at high tide already in Annapolis and Charleston and so forth and so on. So they have some problems to deal with. But interestingly, again, depending what the land is doing, this is Juneau, Alaska. From the tide gauge, sea level is dropping at half an inch a year because Alaska's rising. Grand Isle, Louisiana, sort of off New Orleans, its sea level is going up with 1/3 of an inch a year, or 3 feet per century. So these are two differences. The same ocean, the same level, but it's what the land is doing. I'm going to give complete credit to my wife for this, but I won't point her out in the audience. So we were trying to figure out a way to portray sea level so the average person could understand what 6 inches or 12 inches meant. This did not, however, go in the National Academy report, I have to say. So this is the numbers for 2030, and we put a low of a couple of inches, a medium midpoint of our estimate of 6 inches, but it could be 12 inches. And this is actually from the year 2000 to 2030. So that's only, 14 years ahead of us. By 2050, the low was 5 inches, the midpoint's about a foot, but it could be 2 feet. So 2050 is not that far out. By 2100, maybe 16 inches, the midpoint is 3 feet, and it could be 5.5 feet. But those are big differences, huge differences, again, if you're within a couple of feet of sea level. So there's an organization that deals with San Francisco Bay called BCDC, which dealt with bait fill and construction, and they did some studies beginning of maybe a decade ago on sea level rise, and they took 16 inches of sea level rise, which could be reached by 2050, and this blue, there's SFO, this blue is all the stuff that would be underwater with 16 inches sea level rise. So you don't think about it when you land at SFO. In fact, a plane a couple of years ago misjudged that a little bit. But at 16 inches, the water starts to get out on the runway. Now you can say, that's okay, I'm going to use Oakland. Believe it or not, Oakland is exactly the same elevation. And it's because those airports were built back in the 1940s when sea level wasn't an issue. They were all built on fill, so, God, it's expensive. They're bringing all that rock into it. Let's get it up above high tide and call it okay. And this is Oracle. There's a lot of other big companies with facilities very close to sea level because it's nice to be on the bay. So this is a facility we're not going to give up easily, and I'm not saying, at 2100 we just stop, or 2050. We're probably going to want to protect that for a while, but I think some of the questions we're going to have to ask is, which facilities do we want to hold on to as long as we can, and which ones are we going to say, we don't need that parking lot at beach level. Maybe it's Sea Cliff State Beach, for example. But when it gets to SFO and other airports around the world, many of which are built on fill out over the water, Washington, Reagan, Hong Kong, those are huge investments, and those are problems we're not going to have to deal with, but somebody will. The other point I want to make is that there's both short-term and long-term issues, and we're experiencing those in El Nino years, for example. So this is the tide gauge at San Francisco, at the Golden Gate. It goes back to the 1850s. And you had some earthquakes and stuff in here that sort of shook it up, but basically you can see it's going up at about 7.5 inches per 100 years, a couple of millimeters per year. But you can see these spikes in here, and those are El Nino years. So although this is going up at 7 inches per 100 years and probably will increase, in the meantime, we can have sea level a foot higher for 2 or 3 months during an El Nino. The water's warmer, it's expanded, we've got this sort of bulge of water moving north. So these are more short-term concerns, along with high tides and large waves, than sea level is for the immediate future. But these are now acting in concert. So this is sort of a ramp with those events coming in on top of it over time. And that's the last winter, which actually was, in some places, was at least 6 inches, some places 12 inches above normal. So sea level is rising, the bathtub is overflowing. That's the edge of the continent is being flooded. But we're going to have extreme events. On top of that, we're going to have some big events. So these are just a few local examples. Twin Lakes, during a big El Nino year, it's covered with ocean. Downtown Capitola is almost at sea level, and they have been repeatedly washed over. There is a little wall here, but that wall is being overtopped. It's sort of an exciting place to be at a really high tide. Seascape, which has been rebuilt, but during the 83 El Nino, high tides, El Nino, big waves went right over that wall, wiped out the front of all those buildings. They now have quite an impressive seawall. And then Pacifica, sort of in the news. These were built 100 feet back. It got closer and closer, and then gradually they tried to protect them, and now they're gone. So another lost neighborhood. Generally, that isn't necessarily obvious to people that we have these extreme events. You may know Mission Beach in San Diego, and this was a nice summer picture. And if you looked, you'd say, wow, these are great investments. There's a lot of beach. There's this seawall back here. You could probably pick one of these houses up for a couple $100,000. No way. Probably a couple of $1 million. And anyway, looks great. I'll buy it. The next picture is taken from right there during a big storm in 1988. And when I see a picture like this, I really want to put a caption on it. Particularly this guy, or these people. You know, what are they doing? What are they thinking? But that water came all the way across the beach, over the wall, into their houses. So this does happen from time to time. These are these short-term events. Close to home, Seacliff, great place to park your RV. Dr. Maria? Great in the summer, people love it. You can drive right down the beach, you can picnic, you can camp, and it looks really safe. But in the winter of 1983, a picture, I was standing right there. Another El Nino, the biggest one in maybe 50 years that hit. The waves are bringing logs and debris from Soquel Creek and the San Lorenzo through that structure. RVs are gone. I think that bathroom was wiped out. And when it was all over, well, at this point I left. It's down almost at beach level, and it was done, that wall that was the 8th wall to build there, was half of it was destroyed. So there's a challenge to build things right on the beach, and I'm not saying it's a bad idea. We just need to understand if you're going to build it, you should probably build it strong enough to last or not mess with it. We've been building timber walls there for a long time. Also short-term, something that's been called king tides. Are these the extremes that occur several times a year when the moon is closest to the earth and the earth is closer to the sun? So this is the Embarcadero in San Francisco. There's now something called the King Tide Initiative where people go out with their iPhones and take pictures. So you probably all know the Embarcadero, and that's high tide today. No sea level rise. So this is San Francisco. This is a parking lot in Marin County. Very low. A bike path in Marin County. This guy just looks like John Belushi, doesn't he? Kind of. He's being so cool as his shiny shoes get all wet. And then this guy, I think he's doing a science fair project for high school. He's standing out here photographing this high tide coming in over the wall. I don't know what happened next, but these are these short-term events. This is the guy jumping in the pool. These are going to continue to occur. This is just last winter out on West Cliff. You know, this happens every other year, and you can see water coming up over the cliff. There are, holes opened up, and we spent $250,000 dumping rocks and drainage, and so we're, kind of holding the edge out there. But what next? Where do we go? What are our options? A couple ways that have been proposed or have been enacted. One is ignore it. In fact, North Carolina decided to do something else. They outlawed it. We can build floating cities, and we have a few of those. Sausalito, Holland's doing some of those. Seattle has a few, but I personally doubt that most of the world's people in coastal zones are ever going to live in floating cities. It's not really that cheap. We can build barriers, and that's what we've done so far. Seawalls, revetments, and we're building, Venice is building a multi-billion-dollar floodgate. There's floodgates on the Thames to protect London from high tides and a few others. But after Hurricane Sandy, a number of engineering firms says, we can build these walls for billions of dollars and we'll protect part of Manhattan, but then we can't do Brooklyn, we can't do this, we can't, It's not just New York, but it's Miami, it's Jakarta, it's Mumbai, it's all around the world. These big cities are exposed, so that's a big issue. And what I will tell you that I think will be the long-term solution is managed retreat. Nobody's excited about that, particularly if you live on the beach. Another way of saying it is stepping back gracefully. But people don't do that when you live on the beach. But in the long run, we will get to 10 feet of rise and 20 feet of rise and 30 feet of rise. And thinking about all those millions of people living at sea level, it's a crisis that's going to come that the world has never had to deal with before. A lot of books have been coming out about this topic. This is a friend who's done an interesting book called High Tide. And sort of the closing remarks here are really simple. They're 5 two-word summaries that you can remember and repeat as a mantra. It's real, it's us, it's bad. Scientists agree. Originally I said there's hope, and I added there's some hope if we start soon. And I'll just leave you with a little on the light side of it, that a few more years we can just swim over Eden because steel will fill up the island. Okay, thanks very much. Now Monica will make the judgment.
Yes, we have about 10 minutes for questions. And then maybe, yeah, if there's extra questions, Gary can stick around for a couple minutes. But yeah, about 10 minutes.
So the difference,
Oh, I think you had your hand up first. Go ahead.
the difference between ignore it and managed retreat. I mean, if you ignore sea level rise, eventually you'll have to react. Managed retreat implies some forethought. Tell us a little bit about managed retreat.
So it's one of those concepts that is beginning to take hold in a few places. California has maybe 4 places now that I'm aware of where we've actually started that. One is the Great Highway in San Francisco. So south of Ocean Beach, highway's fallen in. They've actually got a plan. They're going to reroute it inland and let those cliffs move back. Pacifica, not the apartments there, but where the road comes down along the water there before you go up over Devil's Slide. It's a parking lot. I think there's a Taco Bell out there and a few other things. They actually have a plan to let that move back rather than build more rocks or armor. Santa Barbara is actually adjacent to the university campus's Goleta County Beach, and it's been sort of a 2 very heavily armed camps. One who thinks it's the greatest park in the world, marveling Yosemite, and we're going to save it at any cost, so they put lots of rock in there, so then there's a rock wall instead of a beach. And the other group that says, no, let's let nature take its course. And they finally decided to let nature take its course. I was down there 6 months ago, and they're actually taking all the rock out. So they're going to manage the retreat, let it happen. There's a few restrooms and things, but it's pretty low budget. And then Ventura, right near the mouth of Ventura River, is a place called Surfers Point. And again, it's a parking lot and a bike path, and they're actually moving all that back. So those are low budget facilities rather than any really huge investment. So those are the examples I can say in California where managed retreat is underway. But they may be low-hanging fruit in a sense. If you looked at, I don't know, pick another site, where we've got huge investment.
San Francisco Bay, on the edge of the bay. Oakland.
Yeah, margins of San Francisco Bay is a good example.
Billions of dollars infrastructure.
In San Francisco Airport and Oakland Airport and Alameda Naval Air Station, and much of the Malibu coast is another one where they're dealing with a big problem on Broad Beach in Malibu. Right, next question.
The time of the hot earth,
Hot house Earth?
was that around 250 to 60 million years ago? Permian Triassic extinction?
Yeah, the question was the hot house Earth, when did that take place? Whether it was 250 Permo-Triassic. The one I'm most familiar with is the about 65 million years ago, which was called the PETM, for the Paleocene-Eocene Thermal Maximum. And actually it was a colleague up on campus who, from those deep drilling cores, realized there was a rapid change in temperature and fauna, and it looks like there was a huge burp of methane out of the ocean, these clathrates that hold methane. And so carbon dioxide went up in the atmosphere to about 500, doubled very quickly. I mean, maybe over thousands of years. So things got very, very warm. But there have been probably more than one episode. But that's the one I'm most familiar with. So you could be right. Yeah.
Say more about carbon dioxide. Is it a major factor in all of this? Because climate is in dire. Talk about how we need intrinsic part of the Earth's environmental system. We should be arguing against increasing carbon dioxide.
No, there's no merit. No. I think the simple argument is obviously we've created this, what used to be a balanced system between plants using carbon dioxide and producing oxygen, and animals using oxygen producing carbon dioxide. So one could argue, wow, the more carbon dioxide we have, the faster plants grow and more plants grow. I mean, problem is we're cutting them down and harvesting them, so that doesn't, and they've done experiments and said, yeah, more carbon dioxide doesn't really significantly affect how fast plants grow. They still need phosphates and nitrates and other fertilizers. So I think my own sense would be that's sort of a way of getting around the issue of fossil fuel industry that is going to keep burning fossil fuels by making an argument that we need all that we can get. And in a natural environment, as I say, during this period 55 million years ago, it might have doubled, but there weren't any people here. We didn't have cities. We didn't have to worry about sea level. So up until a couple thousand years ago, it didn't matter. You know, the natural system would evolve. So if it wasn't for people, Earth's going to do fine. We're screwed. That was a little rude, I'm sorry.